Welcome to a read-along with Dr. Powell in the book Discrete Perspectives in Mathematics. And this is subsection 224. So this is entitled Truth Consistent Merges. What we're going to be doing is we're going to be taking a collection of atoms, so truth-false, like TTF type statements that deal with a certain set of propositions or statements. And we're going to be looking at that collection and considering the power set of those, of that collection, the power set of that collection as a set. So looking at all the subsets of, or sub collections of these possible atoms that we can have. And everything, single subset can be thought of as a proposition or a logical statement. So what we want to do is we want to look at this power set has a power set structure with implication being like subset of, and has a structure of saying one statement or another statement, which is like unioning, or one statement and another statement, which is like intersecting. So like the statement that this is true and this is true, or the statement this is true or this is true. So those types of statements that could that we're going to be dealing with, we're going to be looking at that whole system and setup, and then we want to apply some merges. But the merges that we want to apply, why do we want to apply a merge? Like, why do we want to merge things together? And we want to, sometimes by merging this whole collection, we can actually see things a little better and make better decisions, and maybe see how to optimize a Boolean algebraic statement, which has to do with logic circuits and optimizing things like that, making them the best structure possible in terms of ands and or gates, other things like that. That's an application which I don't really go into, but there are some nice uses for this. We can see, basically, we can see things in a better way by applying a function to the situation, in particular, a merge, as long as that merge does a few things. And so these are some rules it needs to obey. And I call this a truth consistent merge. So this merge needs to preserve the poset structure of the arrow. It also needs to preserve these operations, union, intersection, or and or meet and join. It also needs to, it can't merge more than one atom to true. Now, what is an atom? Atom is like a like like a sequence of TTF or FFT or something like that. Those, you can't merge two of those to true if what? If they're different, because otherwise one atom says that A is true, where the other atom says A is false. Well, that doesn't work, right? So we don't want that to happen. We also want the full set, so the set of all atoms, to merge to true. What does that mean? That means that the truth actually exists, because the truth is one of the atoms, right? And then we also want this to merge to false. Because our way of saying that a statement is true or false is if there's a particular atom that represents the truth of the situation, and that atom is contained in that set, or the set that's associated with that proposition. So so the empty set doesn't contain anything, so definitely not the truth. So it should just be false all the time. So we want this to hold true, and in particular, we want the image of the full collection and the image of the empty set to never be the same. We want there to always to be at least two different fibers. This is in one of them, that's in the other one. So, in particular, what if there's exactly two? That means that everything has been decided upon. That we've produced a merge that actually makes the decision of true or false for every logical statement that we can come up with in this particular power set type structure model that we have for a particular collection of statements and their true false different conditions. So if we can do that, then everything either merges to the empty set or merges to the full set. Full set is true and empty set is false. And notice in particular that the empty set is a subset of the full set. So since our merge will want to preserve the structure, the post-set structure, and therefore the existence property of this, then since this arrow exists before, it exists after the merge as well. In fact, we could even think of this as false to true, right? False to true. And similar to another Hasse diagram that we saw earlier in another video, for a singleton set, you could just think of false as being 0 and true as being 1. It's the same Hasse diagram as we had before. And we could think of this as representing this right here if we happen to merge everything to a definitive truth or true or false. Okay, so let's suppose that we have subsets of a power of a collection of atoms, and so this collection of atoms so that we have 4 different codes right here as the subsets. Well, that means there's 4 different elements in the atoms. Well, the only way of doing that is if you have something like this. Okay, so 4 different atoms. So that's what these things represent. This one right here represents include this atom. This one represents include that atom. And the 0 means don't include that atom. This one means include that atom. So this is actually like a collection of some of these atoms and so forth. So let's suppose that we have something like this. Then all right, and then we kind of described that. So each position in the subset code discusses the presence or absence of each of these atoms. All right. So we can let a 1 in the 3rd position mean the presence of that atom FT. Okay. So let's suppose that FT is the one atom that merges to true. So no other atom can merge to true, only one of the atoms. So only one of these guys can merge to true in a truth consistent merge. So what does that mean? That means all the other atoms have to merge to false if everything is going to be determined. So if everything is determined, then everything merges to true or false, and particularly the atoms have to either merge to true or false themselves. So that the merge, okay, all right. So okay, it must since it must merge, preserve intersections and unions. Okay, it ends up being a blockout map, and it ends up being a blockout map. So what is it going to block out? Well, essentially, it blocks out anything that it basically blocks out the atom positions that don't represent the true atom in this particular case. Okay, the ones that are actually going to be false for sure, it blocks those out. So the red actually, so like this, okay, so that really the only indication is this atom contained in the set or not? If it's not, the 0, then it's like the empty set, or it goes down that way if it's a 1. So basically it just eliminates everything, so we're only focusing on if it contains the true atom or not. So it really is a blockout merge in that particular case. And this map actually only has 2 fibers. Now, so each fiber has 8 things in it, but it has 2 fibers. These are the two, right? These are the two codomain elements. I mean, the number of fibers is the number of codomain elements here in this surjective merge. Okay. And so then the two different fibers represent either going to true or going to false. Okay. So, all right. So we add on some notation here. Instead of a complement, we're going to use this notation right here. This means this is read as not A, or the negation of A. Looks like negative A a little bit, but not really, because it's not that, so it's not A. Well, that's kind of funny, but yeah, but it's not A is the way we read it. Or it's the idea, kind of the opposite idea of A. So if A is true, then not A will be false, and vice versa. If not A is true, then A is false. Let's see. The subset code for A is 1100. Why is that? Let's just take a look at that. Well, let's suppose that these are the atoms, right? Well, these are the two atoms that make A true, right? Okay. So those are the two atoms that would be included in the set representing A. Okay, then guess what not A would be? It would be 001. Okay. So whether the complement of A emerges true or false is completely opposite how A emerges. All right. Completely opposite because it either contains something or doesn't, just in the opposite way. A logical negation. In fact, let's take a look. Using this, we can actually represent the whole power set of the collection of atoms and as a Hasse diagram. And let's take a look at what this is. So in particular, down here, these are the atoms down below. So this is the one for TT, meaning A is true and B is true. This is the one for FT. So A is false, B is true. This is the one for TF. A is true, B is false. This is the one, B is false. This is the one for A is false and B is false. So in that way, these are actually the atoms, and these end up just being collections of these atoms. And there's different ways of representing them. I mean, we could just take two atoms and union them together, right? And that would be the collection of those two atoms. And we could have done that all across the board. We could just have unions of atoms all over here that would, expression-wise, at least in terms of expressions, some of the expressions would get very big that way. So there's other ways of thinking about it and grouping things. A is a particular collection of propositions, and B is as well. And you can union those, or, not A is also a collection, not B is also a collection. You can union those in various ways. In fact, if you union them in this way, you get the whole set of atoms. Okay. And here is a subset diagram. So thinking of which atoms we're actually using for each of those propositions, it's the same Hasse diagram that we saw before. And here's another way of representing the same diagram. It's not very different than the other one. I think we just changed this a little bit because either A or not A is really the whole set, so it simplifies that. And A and not A, I mean, that's nothing. You can't have an intersection there except for the empty set. All right. So, so what we are doing actually is we're looking at, these are Boolean algebraic expressions. So A and B are like variables, and they can either be true or false. In fact, that's what goes into the codes, or the atoms here, those possibilities. And you notice how there's different ways of representing these things. Okay, I guess we also kind of changed this up a little bit. We used a De Morgan law or something here, or complements, all right, and changed we kind of play with it around a little bit, or maybe not, yeah, we just kind of play with it a bit. Okay, so there's different ways of playing with these things and changing the propositions. Okay, so we did change it a little bit more. Okay, so there's different ways of playing with it, and it's its own algebra of how to make two things be the same, and adjust them, so they are the same, like simplifying expressions, changing expressions, and so forth, so they're equivalent. But the basic idea is that Boolean algebraic expressions are equivalent if their underlying subset code is the same. So the collection of TTFs or whatever else that cause them to be true are the exact same. So okay, and this is just kind of a description of how to get the full set. Okay, and then we also have right here, as we keep going along, this idea of a tautology. So what is a tautology? A tautology is any Boolean algebraic statement that is the same as the top one, or the one that's always true. So which is the full set of atoms. So anything there is equivalent to a tautology. There's different ways of doing that. In fact, here's some basic examples of some tautologies. Okay, now notice how these are colored right here. That's because we're going to be looking at some kind of a merge. Notice how this is a merge with two fibers. Some things are merged to, these things are merged to true, and the empty ones right here are empty, merged to false down here. So the gray ones with the red borders are merged to upward to true, and these are merged down to false. This is an example of a truth-consistent merge where we've merged. Notice there's only one atom that's merged to true, and all the other atoms have merged to false. Okay, so this is an example of what happens in particular when we send the atom not A and B to true. So how could we see this? Well, first of all, everything that's between this and this, we merge these two guys together. Notice that because it preserves partial order, this and this and this are all are between here and here. Let's see, because this is above it, in fact, and this is above it, and that's above it, and let's see, and in fact, even this is above it. I mean, and in between. So just by betweenness property, we actually get this full fiber. This whole entire fiber of what merges to true happens by betweenness here. So since this atom definitely merges to true, then by betweenness, we have that's just a partial order property. We can even use intersection and union property here. This whole thing right here, we get that whole fiber merging to true, in particular now. And now we know that all these other guys merge to false, so they're all coming down and merging to false as well. And that we actually get that these other guys also end up going to false, and we can see that by looking at different relationships in there, but also just by thinking about how the different fibers work as shifts, right? This is one shift of the other, and these are equivalent, in picture and structure. Okay, so let's take a look now. All right, with another type of merge. This is one that has more fibers. I guess 4 different fibers. True. So there's one is true and one is false, and there's 2 other ones that are neither true or false at the moment. They haven't been determined yet. There is still an option or possibility of one thing or the other. And so let's take a look and analyze that for just a moment. Okay, so let's see kind of how this merge came about. All right. Okay, so let's suppose, so it was described right here. All right, so this is a merge where we're just going to send A to true. I guess that's what's happening. So A, and this is the subset code for A right here. So A is being sent to true, and by between this, we have this fiber right here, and then we're just looking at shifts of the fiber all around. Union shifts, if you will. So since A is sent to true, not A is sent to false in this particular way. So we have this right here. So if we take this fiber that goes to false and we union it onto maybe right here, we end up getting the blue fiber. If we union it onto here, we get the orange fiber. So we get basically this green union onto specifics. We get different shifts of the green to fill out to have all the different 4 fibers. Okay, so knowing that A goes, so that this is just assuming that A goes to true. All right. Notice that in particular, I don't even have a single atom that goes to true, right? If one atom goes to true, you actually always will have, you'll have all the other atoms actually have to go to false. And if that's true, we're going to only have 2 fibers. So if we have more than 2 fibers, that means that no atoms have been decided on. We don't know which one is the truth yet, and so we could have potentially more fibers in this particular merge. Okay, all right. So we're kind of looking at that. All right. So, but of course, our goal is rarely to have more than 2 fibers. I mean, in the end, we'd like to either make a decision if something's true or false. But the in-between idea is often very useful when we're simplifying expressions, and that haven't quite been determined yet. In fact, it could be an in-between state of a full, complete determination. So what if we take 2 of our 4 fibers, like this one and this one? So let's go back here. So this is the one, so this looks like the true atom, or the full collection. So this one up here. So let's take this gray. So let's merge the gray together with, so the gray is like one object here, okay? So this is like this is in the domain, but and we're looking at the fiber, right? But when these actually merge together, this will be like one node. And that one node will have an arrow from, it looks like an arrow from orange will go to it because there's an arrow right here. So an arrow from orange. And see, does green go to, see, well, green goes to the orange. So, and green goes to the blue. All right, so we kind of, that could be an exercise for the viewer or the reader to actually draw that out, what that would look like, following the properties of merges preserving partial order. But what if, so in that state where we have those 4 different nodes with arrows, and we take those and we merge 2 of them together, namely this one, and that one. So A and B, which one is that? A and B is the orange one here. So the orange one and the gray one. So merge the 2 together, orange and gray. So if we merge the orange and gray together, then the blue and green would naturally merge together as well. truth consistent merge. Okay, so 4-fiber merge, and so then we have a 2-fiber merge. So gray and green, and actually this composition works very nicely. So we could have done a simpler merge first, and then done another merge, and then finally got down to this one. So sometimes it's nice to do in between merges before we actually get to the chase and decide what's all true and false exactly. We can do something in between, do an in-between step, and look at the 4 different fibers. And that's actually very useful for simplifying expressions, Boolean algebraic expressions. And we'll see why that is. So that's kind of the principle that we'll be using as we simplify Boolean algebraic expressions. Okay. So, all right. So let's look at an example of this. All right. Suppose we have a statement like this: A and not B, and then in parentheses, and this says or B. So what we're going to do is we're going to try to find another way of representing this expression. And we're going to represent it as A or B. Now, there's various ways of doing this, but we're going to talk about some principles that can be used in harder expressions as well as this easy case, or this easier case, perhaps. But so here's kind of the idea of how we're going to rewrite this in a simpler way using these basic ideas. You see A right here. What would happen if we took A and we merged it to 1? Now, what is 1? 1 is going to represent the whole set, okay, or the tautology statement. The tautology statement that's always true, and 0 will represent the statement that's always false, the empty set. So 1 represents the full collection of atoms. Okay, so what happens when we merge A with true, or A with 1? Then when that happens, since this merge preserves ands and ors, then we can make replacements. Okay, you can always make replacements, and what's in the image will be the same. Will be the same. Okay, so we can replace 1 there, and let's see what happens. Since 1 is everything, all right, then 1 and not B. So not B is like a set, and you're intersecting. 1 intersect a set. It's going to be just that set right there. Okay, so this really looks like this, right? Well, what does that look like? Not B or B. Well, let's see, thinking of complements, right? You're going to get the full thing. So it's like B complement union B is going to be the full set, the tautology expression 1. So interesting. When A merges with 1, guess what also merges with 1? The whole expression. If you can find a little sub-expression of your expression that if merged to 1 forces this guy to merge to 1, guess what you've actually done? You've actually shown that this guy is between. It's between the expression you set to 1 and the tautology 1 expression 1. So it's in between the two. So looking back at a diagram here, you've actually, so by setting, so for instance, by setting A to be 1, if it makes your expression 1, that means that your expression lives between A and this, which means your expression is either this or this. So if you had a diagram like this just sitting out right in front of you, and you were able to do these between things really quickly, you could easily pick out which expression it is, and which one it should be, would be in a simpler form. So let's keep looking at this example right here. Okay, so that's what we know so far. It's between this. In fact, setting something, merging it with true All the actually the fiber that you're going to have is actually just that, just by betweenness, and all the other ones are just going to be shifts of it. So this betweenness really helps you kind of decide what's going on with your expressions. Okay, so let's kind of go a little bit further though and see what we could do with that. All right, so okay, all right, we know that so well, what do we know then? That our expression that we're working with is in between a and 1. That means that a is below it, right? So a is like a subset of it, is what it means. So that means we can freely just union it on. I mean, you can union on a subset, it doesn't really do anything. Well, why would in the world would we do that? Well, let's see why. So, because if you union it on, then you can look at what's in here. You see how these are unions right here? And you see how this is like an A intersects something? Well, that means that this is actually a subset of A. Since this is a subset of A, it's actually contained in A. So if something's contained in A and you union it on, it does nothing. It's just A. So in other words, this whole part is just A. So what we've just done is we just simplified the whole expression to A union B. So we decided exactly which one it was. Okay, well, this is a first example of a process that I call sandwich swallowing. It's but it's a lot like and very similar to other procedures that are common and that are done. And in the book it mentions and talks about that more. So I let you look at the book to have some references, namely like the prime implicant method is what it is based on. I'll look at example 2. Okay, all right. I guess we know it's in between A and 1, so we could have known it's okay just from the expression. We just talked about that. And we also know that this as a set contains B. This is higher than above B. So that means it must be A or B. Done. Okay. Yeah. So that would be, so we could have just decided it really quickly. There's a lot of different strategies you can use to optimize or make Boolean algebraic expressions look simpler. So optimizing them just means make them look the shortest you possibly can, pretty much. All right, let's take a look at another one. Let's try to simplify this expression to figure out its simplest form that it could possibly be. Now let's look at betweenness, not to the top. Let's look at betweenness to the bottom now. What if we were to merge not A to 0 to the bottom or to the empty set? Okay, so so let's see what would happen. So if not A were 0, all right, so 0, and then we have 0 or not B. And B, and okay, so let's just take a look at what happens now. Notice, okay, if not A goes to 0, then that means that A must be going to 1. All right, so let's see what happens here. This right here is like empty union not B, so that's like does nothing when union on. So it's just not B. Okay, and this is B union everything, which is just everything. It's just 1. Then so it's the whole set, because if you union anything to something to everything, it's just a subset of it. You're just going to get everything again. So it looks something like this. And you know this is actually 0. Huh. Because something can't be in both not B and B. Ooh, so we end up getting, so we get 0 and 1. And since in preservation of these operations in the merge and think about what the arithmetic is on that simple Hasse diagram with a 0 and a 1. I mean, what's the biggest thing below both 0 and 1? It's just 0. Or 0 and 1, or false and true. I mean, it's just false. So so that tells us that if we force or if we assume and we want to merge not A to false, then what happens? That means this whole expression goes to false. So if you, let's take a look back at that picture and see what that looks like. Okay. So let's see. If we take if we take our expression, or if we take not A, maybe we'll go back here to this. So we take not A and we merge it to false, and that then what we've just shown is that our expression also has to go to false. That actually means that our expression is in between here and false. It's just in this fiber, right? It's in this false fiber. So it has to either be, because it is determined, it's either, in fact, it's determined as at the bottom as being 0. So it has to be either this guy or that guy. I mean, just kind of looking at it that way. So it has to be between there. Okay. So it has to be down that way. So it has to be between. See, how does that betweenness now help us? Betweenness really does help a lot when we're looking at these and determining. In fact, you even saw which two it could possibly be if you're looking at things, with just an A and a B. So let's try to figure out what that would be. All right. So this tells us that not A lies above the expression. So when we intersect something by a set that contains it, remember that nothing happens. So let's take the full expression that we currently have, which is this one. And what we're going to do is we're just going to intersect not A to it. Not A is above it, which means not A is a superset, or it contains the expression that we're working with as a subset of it. So you can intersect with it and won't do anything to it, because if you intersect a subset with something bigger than it, you just get back to the subset again. So really, this doesn't change the expression to intersect on not A. That's what we just shown by betweenness. Now, why would that be important? Well, notice that now we can use the idea that not A actually not A actually is contained in this guy right here. Why? Because this is not A or not B. See that? Not A or not B. It's a union. And not A is actually contained in that union. Okay. And so if you intersect on, and this is a subset of that. So then when you intersect, you just get the subset, right? So this whole part becomes what? It becomes not A. All right. So this part becomes not A. Now, what about the next part? See, this is B. Let's see, B and this. Notice that this guy is actually a subset of this one right here. You can just see that automatically. It's a subset of it. So that means that if you intersect them, the subset will win. So that just becomes B. So you just end up getting this. And notice that was one of the options we could have had. So then we knew kind of what we were aiming for. So we were aiming specifically for, so let's see, where was it? It was in this one. When we assumed that this one right here went to false, and we knew that our expression turned to false, that meant that our expression was limited to the greens. So it had to be either this one or this one, and we figured out exactly what it was using that idea. Okay. All right. Okay, so let's keep going. So this is okay, so in general, let's kind of formalize this process of what we've been doing a little bit. So we'd like to sandwich one expression P between an expression E and either 0 or 1. All right, so if your expression P or a proposition is in between an expression and 1, so if a proposition that we're interested in is in between E and 1, then we know that P is equal to E or P. And if it's between 0 and an expression, then a proposition is the intersection of the bigger set and P itself. So we can make a replacement. We can rewrite our expression. And when we rewrite it, sometimes we can use that rewriting to do some swallowing of like, well, this is a subset of this or whatever else, to kind of to play with it a little bit. And it shortens our expression and makes it simpler. So we have, but kind of the idea, we need to be able to, yeah, we need to be able to, so now, okay, I guess we're going to be using, I guess now in this description, I'm using an E, okay. So you have E and then you have part of an expression. If you take, okay, and so if you have this situation happening, then part of the expression union E is going to be equal to E, okay. And that's in that exactly way. So we're kind of, what we're doing is just talking about the swallowing process. So this is called, so I call this, okay, so sandwich swallowing, all right. Now, and in particular, why don't we click on this and look at this. So this technique of sandwich swallowing, swallower, so I kind of explain it. And right here, I reference you to the Quine-McCluskey algorithm, which is similar to what is happening in the sandwich swallowing process. Okay, so that kind of concludes this little video. And in the next video, we'll talk about some forms that are nice to have for sandwich swallowing, and we'll get to that in the next little video. Thanks for watching.